Hi everyone, this is lecture video 19, and in this video we start a brand new chapter, which is chapter 4. In this chapter we use derivatives to find extreme values of functions to determine and analyze the shapes of graphs and to find numerically where a function equals 0. We also introduce the idea of recovering a function from its derivative. And in the first section, which is the topic of this lecture, we will cover extreme values of functions on closed intervals. And this is a way of showing how to locate and identify extreme values of function from its derivative. Once you can do this, we can solve a variety of problems in which you can find optimal way to do something in a given situation. And finding absolute max-min values of a function is one of the most important applications of the derivatives. Okay, let's start with this definition. Here, f is our function, and we are defining absolute maximum of a function on a given domain. If f of c is the highest value over that domain of your function, then this value is called the absolute maximum value. And if f of c is the lowest value over your domain, then you can call it as the absolute minimum value of your function. And absolute maximum minimum values also called as extreme values. Okay, so let's also highlight this part. Extreme means absolute max-min, max or absolute min. You may also call them as global maxima or minima. And let me draw here a graph for you to visualize what is an absolute maximum value, what is an absolute minimum value. So this is the coordinate axis for us. And let me draw a graph here, like, for example, this one. Okay, let's say this is our y equals f of x function, and over the whole graph, let's say, you see that this graph is continuous for all the real numbers, so the domain of this graph is the whole real line. Over the whole real line, we can see from the graph that this is the biggest value and this is the smallest value, so that you can call this smallest value as the absolute or global minimum value, and this is the highest value. That's why you can call it as absolute or global, again, global maximum value of your function. Okay, let's look at the next example. Okay, in this figure, we see the functions cosine x and sine x. Let's concentrate on the pink one, which is the cosine x. Over this pink graph, we notice that this value 1, which is attained at the origin, is the biggest value of cosine function. Over which domain? Now we are interested over just this closed interval from minus pi over 2 to pi over 2. So over there, for cosine function, this is the biggest value. So this is the absolute maximum value of the cosine function, value of cosine x over which interval? Over the given interval minus pi over 2 to pi over 2. And similarly, the absolute minimum values are these values, which is the value 0. So these 2 points gives us what? Absolute minimum value of cosine x over the given interval minus pi over 2 to pi over 2. Like this. Now we can do the same type of analysis over this graph, which is sine x, and obviously this is the highest value. That's why let's call it as absolute maximum value of sine x function over which domain? This one. And let's search for the lowest value, obviously here. This is the absolute minimum value. What is that value? Minus 1, right? Absolute minimum value of sine x over the given domain. Okay, by looking, and from the graph, it is not that difficult to see the highest and smallest points. So let's do similar analysis for x square function over different domains. So here you see the graph of x square function, and we will be searching for its absolute max and absolute mean over different domains, and you will see that the highest and biggest values can be different over different domains. So over the whole real number from minus infinity to plus infinity. Okay, so the first graph, so we are looking at the whole real numbers over there. So our domain is this one. What is the absolute maximum value? What is the absolute minimum value? So obviously this is the smallest possible value for this graph over the whole real numbers. So this is the absolute minimum value of this graph. Is there any absolute maximum value? So this graph keeps going like that because we choose the whole real numbers. So absolute maximum value, the highest value of this graph, is never attained because of the interval is an infinite interval. So you see these arcs are keep going like this. So there is no absolute maximum value of this curve, which is y equals x squared curve over this domain. No absolute maximum, but there is an absolute minimum value. What is that value? It is 0, and it is attained at x equals 0, of course. So now we will change the domain. This time we look at this closed interval. Our curve is the same, y equals x squared, and we are concentrating on the closed intervals from 0 to 2. This is the domain now, just this part. And now you see that the biggest value over this domain is attained at this endpoint. So what is the value of the absolute maximum? It is 4. So absolute maximum value over the domain, over the closed interval 0 to is 4. It is attained at this endpoint 2. And this is the absolute minimum value, which is 0, and it is attained at the left endpoint 0. Okay, so you see the difference when we change the domain from minus infinity to plus infinity to this restricted one. Then your function obtains its absolute maximum value. Okay, let's play with the domain again. Now I'm excluding the 0 point. Okay, 0 was included here, but it is not included here anymore. We are concentrating on this interval, which is a half open, half closed interval, right? Over this domain, and search for the absolute maximum value, which means the highest value of your graph. It is obviously here. This is absolute max. And search for the absolute minimum value. The graph is getting smaller and smaller towards 0, but is it attained? Is absolute minimum value attained? Since this is not included, 0 is not included in open interval, we see that absolute minimum value is not attained. Is not attained, okay? That's why no absolute mean, because there is a hole there. And if you also exclude the other endpoint, which is 2, now we have open interval. Both endpoints are not included. You see, that's why in this case, the absolute maximum value and the absolute minimum value both are not attained. So not attained because there is a hole there. Also here, not attained. That's why there is no absolute maximum value and there is no absolute minimum value for this graph. So this exercise shows that if you change the interval, the absolute maximum minimum values of the same function may differ. It depends on the domain you work with. Okay, look at here. Now we will cover this theorem, extrema theorem. As always, all the theorems will have some assumptions. If the assumptions are satisfied, then you can apply the conclusion. So let's look at the assumptions here. F is a continuous function on a closed interval, AB. If this happens, then what does it say? Then F attains both its absolute maximum and minimum value. So let me put the assumption box and conclusion box. If F is continuous over a closed interval, this is a very strong assumption, you know, then this is what extreme value theorem is. Extreme value theorem, then the conclusion box is F attains its absolute max and absolute min. So this is our conclusion box. Let's see some visualizations from graphs of how this theorem works. Okay, this is our function y equals f of x, and over the closed interval AB, there is no problem about continuity, you see. So this point is the highest point, absolute max, and this point is the lowest point of it, absolute min. And over this closed interval, by extreme value theorem, we are sure that our continuous function takes its absolute max and absolute minimum value. Or the situation may be like this. By the way, these absolute maximum values here are attained at some interior points, which are x1 and x2. Maybe they may attain at the endpoints, as in this figure. This is the absolute maximum value of your continuous function, for example, attained at one of the endpoints of the interval, and this is the absolute minimum value attained at the other endpoint. These, at this case, maximum and minimum values occurs at the endpoint. Sometimes one of them may occur at the endpoint and one of them may occur at the interior point. Absolute max is here. Minimum is attained at this endpoint, maximum is attained at an interior point, and this is the vice versa of it. This time, absolute maximum value is attained at one of the endpoints, and minimum value, absolute minimum value, is attained at an interior point. This four cases shows you how extreme value theorem works for continuous functions over closed intervals. For all these four figures, the graph is continuous over the closed interval AB. Then let's try to understand what may go wrong if your function is not continuous over that closed interval. Okay, let's look at this function. Obviously, there is a problem at one about continuity, right? So let's emphasize this. At this point one, your function f of x is obviously not continuous. Why it is not continuous? Because the defined value is not the same as the limiting value from left. So there is a jump here so that it is not continuous. That's why, since this assumption doesn't hold now, the assumption of the extreme value theorem does not hold, you cannot expect the conclusion will apply. So obviously, there is no absolute maximum value of this function, right? This is the smallest value. Okay, absolute minimum value is attained at one of the endpoints, but follow the graph. Since this is a hole, since this point is not attained, it suddenly jumps to zero value at the x coordinate. So at this point, it is not continuous. Assumption doesn't satisfy, so there is no absolute maximum value of this function. Okay, since assumption doesn't hold, conclusion also doesn't hold that. So if you read the explanation here, it says that even a single point of discontinuity can keep a function from having either maximum or minimum value on a closed interval, which happens here at this right-hand point. Okay, since the assumptions does not hold, you cannot make sure that there is an absolute maximum value of this function, which is not correct. No absolute maximum value attained here. Okay, so let's talk a bit on local max and local mins. The word local means that you are now analyzing things locally in a neighborhood of a given point, right? So local maximum is what? We are interested at this point C. You look at its neighborhood. If over this neighborhood, the image is the biggest and this, or sometimes it may be the smallest, like here. If over this neighborhood there is no greater value than f of c, then you can call that value as the local maximum of your graph. And for the local minimum, again, you search locally. Searching locally means that you just look at the neighborhood of that point. Okay, you are not looking at the whole domain, but just the neighborhood of it. And over this neighborhood, you see that this is the smallest value. There is no smallest value than this one, so that you can call it as a local minimum. Okay, and similarly for the point D, for example, this is locally the biggest value. That's why it is a local maximum. And at the endpoints, you just look at the neighborhood like that, like half neighborhood from left. This is the smallest value over its neighborhood, and it is called as the local minimum. There is no smaller value than this over this neighborhood, and also for this one. Over here, there is no smaller value, so this is a local minimum. And now if you can search for the absolute and the maximum and absolute minimum. Now, we will look at the whole domain. Obviously, this is the highest point, right? This is the highest point, so it's an absolute maximum. Obviously, this is the lowest, smallest point, so you can call it at the same time as the absolute minimum. So one of the local maximums will be an absolute maximum of your graph. One of the local minimum points will serve as the absolute minimum of your graph, okay? So this is the absolute minimum point. This is the absolute maximum point, global biggest and smallest values. And local ones are found by looking at the local data over this neighborhood. This is the possible greatest value, so you call it as local maximum. That's how you call them, okay? Now, let's consider how we can detect local max and local minimum values. I mean, how we can detect all those points, x equals a, c, e, d, and b. Okay, if you have the graph, you can see them, but without the graph, is there a way to detect them algebraically? I want to emphasize something here. Over these local minimum points, there is something special, right? We have a horizontal tangent line, you know. These are horizontal tangents, so what about the slopes of them? The slope of this line is 0. The slope of this horizontal line is 0. And there is also this point, which is a local maximum point. What is special about it? In one of the lecture videos, we talked about the corners, right? At this corner, since this is a corner point, your function is not differentiable there, so that f of t does not exist there. Or let's say it is not defined because you have a corner, it is not differentiable, the first derivative is not defined there. And similarly, if for the points c and d, since the slope of the tangent line is 0, we can rewrite this information in terms of the first derivative. So f prime of your function at the point c is 0. Slope is the same as the first derivative. Also for this one, f prime e is 0. So this at these local maximum and local minimums, we may either have first derivative 0 or first derivative is not defined. So this is the algebraic way of detecting the points over which local max and minimums occur. Okay, so this is called as the first derivative test. It says that if f has a local minimum or local maximum value at an interior point C, for example, so all those points that are highlighted with green are interior points. So over this green shaded interior points, we have either local max or local min. So how do we detect those points? What happens at C, E, and D? Over them, first derivative is either 0 or it is not defined. So this is the conclusion of the first derivative test. At those type of points, if you have either first derivative 0 or it is not defined. So either f prime is 0 or f prime c is undefined. But you know, this theorem adds one more information, like if f prime is defined, then this has to be 0. So it eliminates this case by putting this assumption here. If it is defined, then first derivative has to be 0. Okay. So we will be using this information a lot for detecting the points over which absolute max min points happen. So let me write a summary about that. If f has a local max or local minimum point at a number c plus f, if f prime c is defined, then what can we say about the first derivative of your function at the point c? Then this has to be 0, because at local max and local minimum points, your function does such a turning. If the graph is turning like this, you must have a horizontal asymptote, meaning that the first derivative has to be 0 there. Okay, this is the conclusion. And this test is called the first derivative test. So this is a theorem. Let me move on. So again, we are emphasizing the similar thing. F has this time extreme values. Now we are not just talking about local max or min, also we include the global absolute max min value. So F attains its local max min or absolute max min values, or this time we are also considering absolute max min values, at which points local max min or absolute max min occurs. We see the answer from this graph, either at the points where you have first derivative 0 or first derivative undefined, or now I'm also considering absolute maximum or absolute minimum, and you can see that they may occur at one of the endpoints, just like happened here. That's why such values occur either the points at which you have first derivative 0 or first derivative undefined, or it may happen at the endpoints of your domain, okay? So this covers all the cases at which you may have local max min or absolute max min values. Okay, now we are ready to define what is a critical point. A critical point is a point at which your function has first derivative 0 or has first derivative undefined. So we talked about these two cases where at the points where you have local max min values. So for these local max min values, first derivative is defined, they are 0. Here, since you have a corner, first derivative is undefined. Such points are called the critical points of your function, okay? So critical points means that either the first derivative 0 or the first derivative is undefined. So we are defining what's the critical point here. So if one of these two cases happen, either the first derivative is 0 or undefined, then they are called as the critical points of your function. Okay, so I'm talking about plural case. Points at which you have either that or that are called as the critical points of your function. Okay, so now I will talk about a strategy, a method to help us to find an absolute max-min values of a continuous function over a finite closed interval. So we will be solving a very certain type of problem here. We are searching for the absolute max or min values of a function which is continuous. We are dealing with a continuous function here over a finite closed interval. So to handle this problem, you can divide your strategy into two steps. First, evaluate the critical points of your function, then make a list of critical points and endpoints, Then evaluate your function at all those critical points and endpoints. You will find the images, and the biggest image will be taken as the absolute maximum value of your function, and the smallest image will be taken as the absolute minimum of your function f. Okay, so let's apply this method over this example. So finding the critical points and the endpoints is the first step, which is the most crucial step of this method. This method is called closed interval method, by the way. Closed interval method. Okay, so find absolute max-min values of this function over this interval. Okay, our function is this one, and we will be dealing with this closed finite interval. Okay, this is a closed finite interval, and we are searching for the absolute max-min values. So the setting fits directly to this case here, searching for an absolute max-min values of a function over a closed finite interval. So this example fits the technique. Okay, now I will be following these steps. First, finding the critical points. Critical points of this function. How do I find it? I need to compute the first derivative. Remember, critical points are the points at which either you have first derivative 0 or first derivative is undefined. So let's compute. This is a product function. You know how to take the derivative of products. You will apply product rule. So derivative of the first function, which is 10 times the second, plus first function stays the same, then you will derive the second one, which is minus 1 over x. Okay, then you do this simplification, right? So what do we have? Let's write the result, minus 10 ln x minus 10. So, sorry, let me write it better. Minus 10 ln x minus 10. Okay, so the first derivative function is 10 parentheses, right? 1 minus ln x, and then we will search for the values at which this expression is 0. Remember, critical points are the points where the first derivative is 0 or undefined. So what are the roots of this equation then? This is being 0 means that ln x minus 1 is 0. So ln x is 1. So x is what? X is solved as e. ln x is 1 at the point e. So this is the only critical point for us. Only critical point. Is there any point at which your first derivative is undefined over its domain? Okay, so no such values. That's why this is the only critical point. Let me also put that part 2. Is there any point where f prime is undefined? From this case, we obtain no point. There is no such point, okay? So This is our only critical point. Now, for the step 2, remember what we do? We will make a list of critical points, also including the endpoints, and we will evaluate the values of function at all those points in our list. So x equals e is the critical point. What are the endpoints of our interval? You see, there is also these endpoints. Okay, this comes from the critical point, and these two comes from the endpoints of the closed interval. So for all of them now, I will evaluate the function. What is f of e? You know, your function is here. If you evaluate it for x equals e, you will obtain this. What is f of 1? It is 20. Just insert 1 for x. And what is f of e squared? You will find 0. Okay. We make a complete list of critical points and endpoints. We evaluate our function at all those points in our list. And now it is time to choose the biggest value, which is this one. This is the biggest value on this list. Biggest value. That's why I will call this value as the absolute maximum value of f. It is attained at which x point? Attained at x equals e point. And the smallest one is this one. This is the smallest value among these images. So I can call it as absolute minimum value of f, and it is attained at x equals e square point. So this is how you should treat such kind of problems. This is a certain type of problem which asks absolute max-min of a function over a closed interval. If this is the setting, you will be using closed interval method, which is summarized here. It consists of 2 steps. First step, find the critical points. So to find the critical points, you will first compute the first derivative, equate it 0, solve the roots. There is also this case. Okay, either this may happen or this may happen for critical points, but there is no point where f prime is undefined. This is our only critical point. Now make a complete list of critical points plus endpoints, evaluate your function at all those points, and then you will choose the biggest value and the smallest value among this list as the absolute max and absolute minimum value. And that's all for this video. I stop here. See you in the next lecture video.